Hello and welcome to my new video, and this one is titled Journal Club or the Joy of P2A. And as you can see, the monkey is wielding a literal journal club, which is not as far from the truth as I think should be, because after all, the name journal club sounds jolly, it sounds happy. Usually, a journal club is a lot more like this, that usually you could almost call it paper criticism club, because usually you take a perfectly good paper and try and find the Achilles heel in it, which, yes, okay, it is the scientific method, but it still feels a little mean-spirited, or at least false advertising. I mean, if they called it Journal Criticism Club, then I feel it would be a lot more accurate, and maybe people might attend more if they're so inclined. But in this particular case, the paper that I will be journal clubbing is a paper written by a dear friend of mine, which I helped in because I'm among the authors as well. And okay, quick crash course in OGT if you haven't been watching my previous videos. OGT stands for O-glutamate transferase, and it exists in mammals and fruit flies and all kinds of other organisms, and it is very tightly regulated. It applies the O-glutamate sugar to a smorgasbord of proteins with a, quite frankly, dazzling array of functions. And as we discovered in the course of our research and in the course of DNA testing becoming cheaper, mutations in OGT cause CDG, or congenital disorders of glycosylation, which cause a variety of symptoms, including mental retardation and also various other things, including epilepsy, of all things. But crucially, also, deletion causes death. So, let's not get bogged down too much in this visual abstract, because quite frankly, it's unintentionally confusing, but it does feature teasers of some of the stuff coming up. Because here we have, yet once again, the pointer in Woodstock mode. This is the rough approximation of the structure of OGT, because it hasn't been structurally analyzed in one chunk. It's been analyzed in the catalytic domain and in the TPR domain, or tetratricopeptide domain. Point is, they've patched this together like a jigsaw. But anyway, point being, mutations are logged, and we want to find a dynamic and clever way of studying them. And how do we go about that? So, yes, okay, ignoring what's on the screen right now, we have expressed it in bacteria and done biochemical characterization, but it would be much better to actually analyze it in situ, in life. So, we rolled up our sleeves and got our CRISPR on and introduced superfolder GFP at the C terminus of the wild-type OGT allele. So after carefully checking that everything was in order, and the OGT really didn't mind having its C-terminal monkeyed with, I'll do a subsequent video on termini later. Point is that OGT does not mind, and as a result, this strain produces a slightly larger version of OGT, which has superfolder GFP at the end, which serves many purposes. After all, it makes, well, the cells glow, obviously, but it is linked to OGT's proteinic level. So, the level isn't that high. Point is, we did first a standard battery of tests to check, hey, is the level of OGT, the protein itself, the same with or without the tag? The answer is pretty darn similar. No significant difference. Similarly, the level of the actual O-glutamate modification in the cells, similar. Great. This was just the proof of concept. Now moving forward to actual testing. So we did the first due diligence step was to check the effect of drugs that alter this system, because OGT adds the glutamate sugar. However, OGA, O-glutamate acetylase, cuts the sugars off, and they exist in an equilibrium. However, if you apply, for example, the inhibitor thiamet G, known to its friends as TMG, that inhibits OGA, so it gives OGT an easier time. As a result, because the counterbalance isn't there, the level of O-gluconacylation goes up in the cells. Yay! And similarly, if you apply an OGT inhibitor, the cells will actually try and counter this by making more OGT protein, and still, despite their best efforts, because, a pile of protein is still being whacked about by an inhibitor, the level of O-gluconacylation itself goes down. So, yeah, not so easy to see in a Western blot, but with this graph, you see how OSME4 pushes down the level of O-gluconacylation, but the protein is cranking up, desperately trying to redress the balance. And conversely, when OGA is inhibited, OGT does try and give OGA a bit of a break because it's feeling bad for its antagonistic partner, so it goes down, just as the level of O-glutenacylation goes up because, Mother Nature can only stretch so far. The equilibrium will only rebalance to a certain extent before it just goes, I'm sorry, this is the best I can do, deal with it. Anyway, now, that's all very exciting, but we wanted to go and take a voyage into the clinical mutations that we were charting and wanting to get an insight to. And it's one thing to introduce them all individually to cell lines by CRISPR, but that's a little labor intensive. And since they keep on popping up like whack-a-mole, it's getting kind of intense. So the alternate, quickly an aside before I got ahead of myself. Here we actually do FACS sorting of the whole population, and to check basically, those are harder to see because you have to go blind staring at the axes. But the point is, the population shifts. If you give them just DMSO, so no treatment, this is the level of GFP, so that's your OGT level, while it goes up in the case of OSME4, and it goes down in the case of thymate G. So you have your benchmarks of the cell's reaction, and you have a image of the cell itself, well, a cell. You get the picture. Now, moving forward to our voyage into the mutations, because if you already have a cell that's expressing GFP, giving you a gauge of how the cell feels about the O-glutenac balance and about the OGT-OGA equilibrium, we then thought, okay, why don't we transiently transfect in a plasmid that expresses more OGT, so we artificially augment the level of OGT. How is the cell going to feel about that? Is it going to alter the situation in response? But because transfection, and I haven't gone too much into this before, it's a statistical process. So first we did a mock transfection to illustrate how many cells are actually transfected in the whole population. So this vector here, it just expresses BFP2, basically. And so, first there's untransfected with the cells where they don't express any BFP. But when you smack them with the mock transfection plasmid, you get some, but not all, is the point. So you have this gated population that are being altered partly. So that's one thing to see. But now we want to see the consequence of adding OGT at the same time. So this is why I gave the title of the talk as The Joy of P2A, because the P2A is actually stolen from viruses, and it's a clever way of making a single promoter produce two different proteins. Because first, the CMV promoter, cytomegalovirus, it expresses the OGT that is lovingly cloned into this vector. Then, when the ribosome doesn't hit a stop codon, because there's no stop codon here, this is important, it runs into the P2A sequence, and this is a magical secret code that causes the ribosome in mammalian cells to stutter. And this stuttering, most of the time, causes just the protein to be ejected. So, boop, there goes OGT, released into the cytoplasm. However, a percentage will continue on, starting afresh, going, well, that was weird, I'm going to continue now, and produces BFP. So you get a proportional amount of OGT and some BFP relating to how much transfection you see. So that allows you to do the gating like we did with the mock transfection to show, okay, some of these guys do have OGT being expressed, but you can ignore the ones that aren't. Anyway, so this is only looking at the GFP, and you see, oh yes, GFP on that axis, BFP on this axis. So you see BFP for transfection. Yeah, the mock goes up because that's like, hey, we're expressing a plasmid. While without any tag, you see a population shift and produce less OGT because there's an excess of OGT. But that's confusing because it's better to actually have a little indication of where the transfected are. So here we see OGT wild type. The cells go up in BFP as well as down in endogenous OGT expression. So this is gauging how do the cells feel about this uninvited guest. They realize it's producing functional OGT, and so they crank it down. And conversely, as a negative control, this is a catalytically inactive version of OGT. The BFP goes up, but it barely goes down in terms of OGT level. So that gave us data on two populations. So, okay, we got, this is the alternate image where rather than it being different axes. Point is, this gated data allowed us to gather this here graph, and this is the important bit. When we get past all the facts data, which is a little hard on the eyes, we saw, okay, mock transfection, here is the relative level of OGT. But if you provide loads of OGT wild type, down goes your OGT level. But if you provide the catalytically inactive, it still goes down, which is a little bit puzzling, but the point is it goes down significantly less. So this gives you a response curve almost that, okay, that's if introduced guy is completely wild type, that's if it's inert. So now you have your 1 and 0 benchmark. So this is the real meat of the paper, where we took loads and loads of different mutations, some of them clinical, some of them theoretical, and basically did the same test. The K to M mutant, inactive, and the wild type versus how do you feel about this? And this gave us, okay, various ones with various levels, which we measured. It's all about the reactivity. So the reason I brought forward this paper is partly because it's a really cool proof of concept, and it's a collision of several systems. You have a really cool CRISPR insertion, which allows you to measure in a living, breathing, growing cell the OGT protein level, which, it's away from Western blots, it's away from a quantitative RT-PCR. The point is, it allows real-time measurements, so you can literally introduce something, watch the population change, introduce something else, watch the population change. So that's where it has value. And on top of that, you have a trackable transfection, which allows you to gather data by facts. So yes, I'm biased because I was deeply involved with the production of this paper, but I just thought it was a really, really cool concept to mention. And hey, if you have any questions, as ever, I encourage you to ask. Check out the links in my bio. Check out my other videos for that matter. And yes, if you're encountering strange urges of generosity, feel free to buy me and the Purple Monkey a coffee by following this link. And thank you for watching.